Hello there, and welcome. Tonight, our quiet journey will gently carry us into the boundless wonders of the cosmic expanse, a realm so profoundly vast that our human minds can scarcely begin to truly grasp its magnificent scale. Out there, far beyond the familiar boundaries of our own solar system, the universe hums with an immense and ceaseless activity. For countless billions of years, entire worlds have been brought forth and then transformed or undone within a cosmic cycle that seems potentially infinite in its slow, unfolding rhythm. Astronomy provides us with a rare glimpse into this miraculous and ever-changing world, a place where colossal stars can collide with unimaginable and silent power, where planets, like silent wanderers, drift through the endless darkness between distant suns, and where invisible forces gently yet profoundly warp the very fabric of reality itself. We find ancient galaxies that defy our current explanations, colossal black holes that appear to bend and even break the fundamental laws of physics, and an uncountable host of other wonders still patiently waiting to be slowly discovered by our searching gaze. This channel is dedicated to these quiet journeys through knowledge to help curious souls find their way to rest. Now, let us gently begin our exploration. Stars, those distant, shimmering jewels in the velvet blackness, can erupt in a sudden and glorious burst of energy. Their explosions possess a power so immense that, for a fleeting moment, they can completely outshine the combined radiance of entire galaxies. Imagine a star many times more massive than our own familiar Sun. Throughout its long and brilliant life, this stellar giant has been tirelessly fusing lighter elements like hydrogen into heavier ones such as helium, then carbon, oxygen, and beyond, deep within its scorching heart. This process, this stellar alchemy, generates an enormous outward pressure, a constant push that perfectly balances the relentless inward pull of its own overwhelming gravity. But eventually, after eons of this delicate dance, the star's core becomes a dense and inert sphere, primarily composed of iron. At this critical juncture, a profound change occurs. Iron, unlike the lighter elements, cannot release energy through fusion. In fact, any attempt to fuse iron would actually consume energy rather than produce it. This means the star has exhausted its ultimate fuel source for maintaining that crucial outward pressure. Suddenly, the delicate balance is irrevocably broken. The immense weight of the star's outer layers now has no opposing force to hold it at bay. Gravity, that silent but absolute victor, begins its inevitable triumph. The core succumbs to this crushing force and begins to collapse inward at truly unimaginable speeds. Within a mere fraction of a single second, this inward plunge is so rapid and so violent that it crushes all matter within the core into a state of extreme density, a state far more compact than anything we could ever hope to experience here on our gentle Earth. The protons and electrons are literally squeezed together to form a vast sea of neutrons. This super dense material, called neutronium, is so tightly packed that a single teaspoonful would weigh billions of tons. Then, in a spectacular rebound, this incomprehensibly dense core suddenly pushes back. An astonishing and powerful shock wave is generated. It races outward from the core, tearing through the star's remaining outer layers with incredible destructive force. Enormous quantities of energy are unleashed, flooding into the surrounding space. This energy takes many forms. It streams forth as blinding light, as searing heat, and also as cascades of ghostly particles known as neutrinos. These elusive neutrinos, generated in staggering numbers, are so weakly interacting that they can pass through almost everything, even entire planets, without a trace. They are silent messengers from the heart of cosmic cataclysm. For a brief but magnificent period, this single dying object, this solitary star, can blaze with a brilliance that surpasses the combined light of billions of ordinary suns within an entire galaxy. Its fiery farewell is a beacon across the cosmic ocean. The sheer power of this blast is so immense that it utterly tears the star apart, flinging all of its enriched material outward into the vast and awaiting expanse of interstellar space. This debris, this cosmic shrapnel, carries with it newly forged elements. Elements like carbon, oxygen, silicon, and iron, which were created during the star's life, but also heavier and more precious elements like gold, silver, uranium, and platinum, which are formed during the supernova event itself, in the extreme conditions of the explosion. These heavy elements are the building blocks, the very atoms that will eventually become part of other stars that will slowly condense into new planets, and perhaps even form the intricate chemistry of living beings, who in some distant future might look back and study the long faded flash of that ancient stellar death. It is a profound and silent cycle of cosmic creation from destruction. Planets, those worlds, both familiar and strange, sometimes find themselves drifting quite freely through the cold and silent void of space. They roam without a star to warm them or to illuminate their solitary paths. These rogue worlds, these solitary wanderers, are believed to be born within planetary systems much like our own. In the early, chaotic stages of a young system's history, newly formed planets engage in a complex and often violent dance. They jostle and tug on one another with their developing gravitational fields as they circle their central glowing star. If this cosmic ballet becomes sufficiently chaotic, if the gravitational pushes and pulls become too extreme, one of these nascent worlds can be flung outward with such incredible speed that it entirely escapes the gravitational embrace of its birth star. It is then cast loose into the deep, interstellar darkness. Once expelled and truly free, it embarks on an endless journey, traveling through the vast and desolate spaces between stellar neighborhoods. Its surface is illuminated only faintly by the distant and scattered glow of faraway suns. Without the steady life-giving light from a nearby star, its outer layers, its entire surface, may freeze solid, forming a crust of permanent and unyielding night, a silent, frozen world drifting in the dark. Yet, deep inside, hidden beneath that icy and perpetually dark shell, there may linger leftover heat. This warmth could stem from the very process of its formation billions of years ago, or perhaps from the slow and patient decay of radioactive elements within its rocky core. This internal warmth can persist for aeons, for billions of years, keeping its interior surprisingly warm. Some researchers even dare to imagine that thick atmospheres might cling to these dark worlds, or that vast, buried oceans of liquid water or other solvents could exist hidden deep beneath the surface. Within these hidden oceans or deep underground reservoirs, whatever complex chemistry might unfold in that protected and secret warmth as the planet continues its silent and solitary wander through the cosmic void. These cold but potentially vibrant places are a testament to the unexpected resilience of planetary evolution. Black holes, those enigmatic and profoundly dense objects, can spin with such astonishing rapidity that they literally drag the very fabric of space and time around them. Imagine the universe's tapestry being twisted and pulled into an invisible vortex. When a massive object, such as a dying star, collapses to form one of these extreme and compact remnants, it retains not only its colossal mass, but also a significant portion of its original rotation. If this inherited spin is fast enough, the region immediately surrounding the black hole transforms into a swirling and turbulent whirlpool of warped spacetime. This phenomenon is known as frame dragging or the lens-tethering effect. Anything nearby, any gas cloud, any passing particle, any stray photon feels this profound and irresistible twisting. Space itself is compelled to rotate, to swirl along with the black hole's spin. It pulls all surrounding matter into a spiraling motion, a cosmic dance that no engine, no force could ever hope to recreate or withstand. Closer and closer to the heart of the black hole, there exists a specific zone, a boundary where nothing, absolutely nothing, can remain still relative to the distant and unmoving universe. Even light, the fastest thing we know, is forced to swirl around, caught in this rotating and dynamic geometry. This extraordinary region is often called the ergosphere. Within the ergosphere, it becomes possible for energy to be extracted from the black hole's immense spin. This extracted energy can then feed the formation of powerful jets of high-energy particles that erupt from the black hole's poles and stream outward across vast distances. It also contributes to the emission of intense, high-energy radiation from the swirling, accretion disk of infalling matter. In this subtle but profound way, the invisible rotation of a compact and unseen object can exert a monumental influence on its entire cosmic neighborhood. It shapes the growth and the dynamic behavior of its host galaxy over truly immeasurable and long ages, a silent but powerful sculptor of galactic destiny. Beneath layers of ancient and unyielding ice, certain moons, those silent companions to giant planets, harbor hidden oceans. Oceans deeper and more vast than any ever found on our own water-rich Earth. In our very own planetary system, several small bodies gracefully orbiting our gas giant planets reveal cracked and frozen surfaces. These icy exteriors are often marked with intricate ridges and mysterious streaks. These enigmatic patterns, these silent scars, hint at something active and flowing, moving just beneath their frigid exteriors. Careful measurements of their subtle magnetic fields and their gravitational pulls strongly suggest the presence of immense reservoirs of liquid water. These vast subterranean seas are concealed beneath thick shells of ice, which can be tens of kilometers in thickness. A frozen barrier protecting a liquid heart. In these dark and sunless oceans, there is no direct sunlight to drive the familiar forms of photosynthesis that sustain life on Earth. Yet, energy, that essential spark, can still come from other sources. As the Moon follows its orbital path around its colossal parent planet, the changing and relentless gravitational pulls flex and stretch its entire interior. This constant stretching and squeezing generates heat through tidal friction, a gentle but continuous kneading that warms the Moon from within. This internal warmth is often sufficient to prevent water from freezing solid, even though the Moon may lie far, far distant from the Sun's diminished warmth. On the rocky seafloor of these hidden oceans, hot hydrothermal vents, much like those found on Earth's ocean floors, may pour forth mineral-rich fluid into the surrounding water. creating environments where complex chemistry, the very precursors to life, could potentially thrive in the perpetual gloom. These hidden oceans, these secret worlds, remind us that habitable environments, those places where life might take root, could be far more common than we once thought. They might exist in unexpected places that from the outside appear cold and utterly lifeless. A quiet testament to the universe's endless capacity for surprise. Galaxies, those swirling and majestic islands of stars, can race toward one another at truly unbelievable speeds. Gravity, that fundamental force, does not simply pull on nearby objects. On the grandest scales, the scale of clusters and superclusters, entire swarms of galaxies move and dance under each other's collective and powerful attraction. Over immense stretches of cosmic time, this slow and relentless motion can bring two enormous star systems together on a gradual, but ultimately unavoidable, collision course. Though their individual stars are spaced so widely apart that direct impacts between them are exceedingly rare, the mutual gravitational pull between the two galaxies profoundly distorts each galaxy's shape. Great streams of stars and vast clouds of gas can be drawn out into elegant and luminous arcs or into long, stretching tails. These stellar rivers can extend for hundreds of thousands of light years across the intergalactic void. As their colossal clouds of gas pass through and interpenetrate one another, they can compress and ignite sudden bursts of intense, new star formation, transforming the very appearance and structure of both colliding systems. Eventually, after a complex and graceful gravitational dance, a cosmic pas de deux that can last for hundreds of millions of years, the two galaxies can merge into a single, larger structure. What began as separate, swirling islands of stars, each a distinct cosmic city, becomes one more massive, and often more rounded and serene celestial metropolis, a silent and slow amalgamation of stellar destinies. Some stars, those dimmer and more enigmatic objects, can cool so dramatically over eons that they begin to resemble giant planets. They occupy a twilight category, a liminal space in the grand tapestry of stellar evolution. Not every object that forms from a collapsing cloud of gas and dust becomes hot enough in its core to sustain the vibrant and continuous nuclear reactions that power ordinary suns like our own. Some simply fall short of that critical threshold, that ignition point, and instead settle into this peculiar, intermediate state. They can begin their long lives relatively warm and modestly bright, but then they slowly and patiently release their stored heat into the cold of space, fading and cooling over immense stretches of billions of years. As their internal temperatures steadily drop, their visible light gradually weakens. Their emission shifts from visible wavelengths into the infrared, a spectrum we cannot see but can detect as warmth. Their atmospheres can contain exotic clouds, not of water vapor, but of metal-rich grains or tiny droplets of strange compounds. They might even harbor exotic molecules that simply cannot survive in the searing infernos of true, active stellar furnaces. At certain stages of their prolonged cooling, their spectra, the unique fingerprints of the light they emit, and their very colors, become strikingly similar to those of enormous gas giant worlds. Yet, these objects are not, strictly speaking, planets. This is because they formed on their own from the direct collapse of gas clouds, rather than accreting in orbit around a larger, more dominant star. They occupy a fascinating space between familiar categories. They illustrate, with quiet elegance, that nature's creations do not always fit neatly into our simple and convenient labels. They are the cosmic in-betweeners, revealing the rich diversity of the universe's inhabitants. Comets, those ethereal and icy visitors from the far reaches of our solar system, often carry complex organic molecules. These molecules are ancient, having formed long before our own sun even began to shine. These celestial snowballs are thought to be pristine leftovers from the vast and swirling cloud of gas and dust, the primordial nebula that slowly collapsed to build our entire planetary system. Within that original and frigid cloud, tiny, solid grains of dust served as surfaces, like microscopic workshops, where individual atoms could stick together and react in the extremely cold conditions of deep space. Over immense stretches of time, simple substances such as carbon monoxide and methane were gradually transformed through subtle chemical processes into more complex compounds. These new molecules often included long chains and intricate arrangements of carbon, hydrogen, oxygen, and nitrogen atoms, the very elements that are fundamental to life as we know it. When clumps of ice and dust slowly assembled into the hearts, the nuclei of future comets, they effectively locked in and preserved this ancient and complex chemistry, like cosmic time capsules floating through the void. As a comet on its long elliptical journey nears the warmth of a star, its frozen surface begins to warm. This warming causes the trapped ices to sublimate to turn directly from solid to gas, releasing streams of gas and fine dust into a surrounding luminous coma and an extended, beautiful tail. By carefully studying the light from these spectacular outflows, scientists have been able to identify a remarkable range of organic materials, including some compounds that bear a striking resemblance to the fundamental building blocks used by living cells. Amino acids, sugars, and even nucleobases, the components of DNA, have been detected. These extraordinary findings strongly suggest that the essential ingredients for biology, for the very spark of life, can form quite naturally in the deep and cold environment of space. Long before any particular planet even emerges from the swirling primordial material. Nebulae, those vast and breathtaking clouds of gas and dust, can glow fiercely with vibrant colors when newborn stars ignite within them. These stellar infants flood their birthplaces with intense and energetic radiation. In certain regions of the galaxy, clouds of hydrogen and other gases are sufficiently dense to begin the process of spawning a new generation of stellar objects. As the most massive and most brilliant of these young stars finally ignite, they unleash torrents of energetic, ultraviolet light. This powerful radiation streams outward into the surrounding cloud and strips electrons from the hydrogen atoms, creating large volumes of ionized gas, a plasma, that vibrates with newfound energy. When these free electrons later recombine with their protons, they release photons of light at specific wavelengths. These emissions produce the rich and luminous colors that we can see through our telescopes. Hues of crimson, azure, and emerald painting the cosmic canvas. The resulting luminous region can span many light years across the heavens, displaying intricate shapes and delicate filaments formed by the complex interplay of gas density, the powerful winds from the newborn stars, and the relentless pull of gravity. Dark lanes of obscuring dust may snake through the glowing material, casting sharp and dramatic silhouettes against the bright and colorful backdrop. Over time, the combined influence of this intense radiation and the energetic outflows from the embedded stars can gradually erode the original cloud, carving out vast bubbles and hollow cavities, eventually dispersing much of the gas and dust back into space, leaving behind a newly formed star cluster as a testament to its fiery birth, a silent and slow transformation of cosmic dust into shimmering light. Extreme and powerful gravitational forces can subtly stretch entire planets into elongated or egg-like shapes. This profound distortion occurs when a world orbits very close to a massive and gravitationally dominant companion object. The gravitational pull exerted on the planet's near side, the side facing its companion, is significantly stronger than the pull on its far side. This crucial difference in gravitational attraction creates powerful tides, not only in any surface oceans that the planet might possess, but also in the solid rock of the planet itself. Over long geological periods, these relentless tidal forces can slowly but profoundly reshape the planet's overall figure, drawing material toward the line that connects it with the object it orbits. Instead of maintaining a nearly perfect spherical form, such a planet may bulge noticeably. Its longest dimension will point directly toward its gravitational master. The constant flexing and internal straining of its interior generates heat through friction. This internal warmth can alter its geology, driving potentially intense volcanic eruptions or powerful tectonic activity deep beneath its distorted surface. Its atmosphere, if one is present, can also respond to this unusual geometry, developing strong and persistent winds and complex global circulation patterns. Observations of these distorted worlds, these silent, cosmic testaments, provide astronomers with a natural laboratory, a rare opportunity for studying gravity's powerful influence on solid matter under conditions that simply cannot be replicated or even approached in our laboratories on or near Earth. These worlds are silent witnesses to the immense power of cosmic tides. Pulsars, those astonishing objects, emit perfectly timed beams of intense radiation. These beams sweep across the sky with remarkable precision, like cosmic lighthouses guiding unseen ships through the stellar seas. These extraordinary objects are the rapidly spinning and incredibly dense remnants of massive stars that concluded their lives in catastrophic supernova explosions. What remains after such a violent demise is an incredibly compact core, a sphere with a diameter comparable to that of a small city, yet containing more mass than our entire Sun. This compact core spins with astonishing speed, sometimes rotating many hundreds of times each single second. It also possesses an immensely powerful magnetic field. Charged particles trapped near these magnetic poles are accelerated to incredibly high energies. As they accelerate, they emit tightly focused beams of radio waves or even higher energy radiation like X-rays or gamma rays. As the object, the pulsar, rotates, these narrow beams sweep through space. And if one of these beams happens to pass across our line of sight, across our position, here on Earth, we detect a precise and regular pulse of emission. The intervals between these pulses can be stable to a truly remarkable degree, rivaling the incredible precision of atomic clocks. Astronomers use these regular and dependable signals to test fundamental theories of gravity, to probe the intricate distribution of matter within our own galaxy, and even to explore the subtle ripples in space-time. The gravitational waves produced by distant pairs of orbiting stellar remnants. Pulsars are the universe's most precise and enigmatic clocks. They are celestial wonders that hold within them the extreme physics of stellar death, a cosmic symphony of gravity and magnetism played out on a stage of impossible density. To truly appreciate these silent marvels, we must briefly consider their dramatic birth. A massive star, many times the size of our Sun, burns through its nuclear fuel at an astonishing pace. For eons, it balances the outward push of fusion against the crushing pull of its own immense gravity. But when the core becomes a sphere of iron, no longer able to sustain energy-producing fusion, the star faces its inevitable end. In a fraction of a moment, the core collapses inward with such overwhelming force that protons and electrons are squeezed together into neutrons. This rapid and violent compression creates an incredibly dense object known as a neutron star. It is the remnant core of the exploded giant. The outer layers of the star are then blasted outward in a brilliant and destructive supernova, leaving behind this tiny but extraordinarily heavy stellar corpse. Imagine taking the entire mass of our Sun and compressing it into a sphere no larger than a typical city, perhaps just 20 kilometers or about 12 miles across. That is the mind-bending density of a neutron star. A single teaspoonful of its material would weigh approximately 6 billion tons. It is a state of matter so extreme that even our most advanced laboratories cannot begin to replicate it. The atoms, as we know them, are utterly crushed out of existence, replaced by a sea of tightly packed and degenerate neutrons. The rapid spin of a pulsar is a direct consequence of its formation. Before the collapse, the massive star had a certain rotational speed. As it shrinks dramatically to the size of a city, the principle of conservation of angular momentum comes into play. Much like a spinning ice skater who pulls their arms inward and then spins much faster, the collapsing star accelerates to incredible rates. Some pulsars can complete hundreds of rotations every single second. A dizzying and silent bullet in the cosmic dark, these spinning remnants also possess exceptionally powerful magnetic fields. These fields are thought to be generated by the rapid rotation of the star's electrically conductive interior plasma during its life, and then they are immensely amplified during the core collapse. The magnetic field of a typical pulsar can be trillions of times stronger than Earth's magnetic field. It is an invisible cage of immense power, trapping and guiding charged particles from the star's surface. These particles, accelerated to nearly the speed of light, are channeled along the magnetic poles. They emit focused beams of electromagnetic radiation. These beams are not always aligned with the star's rotational axis. So, as the neutron star spins, these beams sweep across the vastness of space. When one of these beams happens to cross our line of sight, we observe a brief but regular flash of emission, a pulse that repeats with incredible and unwavering precision. This is the famous lighthouse effect. The radiation from pulsars can manifest across various wavelengths. Most commonly, they are detected as powerful radio pulses, but some also emit in X-rays and even gamma rays. These different forms of light carry crucial information about the extreme conditions within these objects. Astronomers use pulsars for a remarkable variety of scientific endeavors. Their extraordinary timing precision allows them to act as cosmic clocks. They are used to test the predictions of Einstein's theory of general relativity with exquisite accuracy. For example, the Hulse Taylor binary pulsar system, where two neutron stars orbit each other provided the first indirect evidence for the existence of gravitational waves. The orbital period of this system is observed to be slowly decaying, exactly as predicted by the energy loss due to gravitational radiation, a silent and subtle ripple through space-time. Pulsars are also being used in ambitious projects called pulsar timing arrays. These arrays monitor the precise arrival times of pulses from many different pulsars spread across the galaxy. Minute deviations in these arrival times could signal the passage of ultra-low-frequency gravitational waves rippling through the fabric of the universe. Such waves would be produced by the mergers of supermassive black holes in the hearts of distant galaxies. A quiet search for the universe's deepest vibrations. There are different categories of these fascinating stellar remnants. Millisecond pulsars, for instance, spin at exceptionally high rates, sometimes hundreds of times per second. They are thought to have been spun up to these extreme velocities by accreting matter from a companion star in a binary system. The infalling gas transfers angular momentum like a cosmic torque wrench, spinning up the neutron star. Then there are magnetars, a particularly exotic and intense type of neutron star. These objects possess magnetic fields that are hundreds or even thousands of times stronger than those of regular pulsars. Their magnetic fields are so powerful that they can literally distort the atoms on their surfaces. Magnetars are prone to sudden and violent outbursts, releasing colossal amounts of energy in bursts of X-rays and gamma rays. These star quakes are thought to be caused by sudden rearrangements or fractures in their incredibly dense and rigid crusts due to the immense stresses of their hyper-strong magnetic fields. The study of pulsars provides us with invaluable insights into the behavior of matter under the most extreme conditions imaginable. Conditions that stretch the very limits of our understanding of physics. They are silent but powerful reminders of the dramatic and profound transformations that unfold in the cosmos far beyond our everyday experience. Each precise tick of a pulsar is a whisper from the edge of what we know. Now, let us gently shift our gaze from these incredible stellar remnants and turn our attention to the colossal and vibrant worlds of the gas giants. Gas giant planets, those immense and swirling spheres of hydrogen and helium, can brew storms. Storms of truly epic proportions. Tempests larger than our entire Earth that refuse to fade, persisting for centuries or even millennia. Imagine the colossal atmospheres of these worlds. Towering layers of gas that endlessly move and churn under the profound influence of deep internal heat and the rapid rotation of the planet itself. These are worlds without a solid surface as we know it. Instead, the atmosphere gradually transitions from a dense gas to a liquid, and then to a metallic state deep within the core. The clouds in these alien skies are made of substances that would be exotic and entirely unfamiliar on Earth. We speak of ammonia ice, methane ice, and even crystals of more complex compounds, like ammonium hydrosulfide. These substances condense under the extreme pressures and frigid temperatures of the upper atmosphere, creating bands of color and intricate patterns that stretch across the entire planet. These vast layers of gas slide past one another at different speeds due to the planet's rapid rotation. This phenomenon, known as differential rotation, creates powerful shear zones, regions where intense turbulence begins to grow and then gradually organize itself into immense atmospheric gyres. These swirling systems are not simply surface phenomena. They are rooted deep within the planet's interior, drawing energy from the heat that rises from the core. Some of these rotating systems, these colossal storms, gather more and more momentum over immense stretches of time. They pull in vast amounts of energy from the planet's deep interior, sustaining themselves against the forces that would otherwise cause them to dissipate, because there is no solid surface to disrupt them, to break their swirling rhythm. They can persist for centuries or even longer. Unlike terrestrial storms, which quickly lose energy when they encounter landmasses, these cosmic tempests know no such impedance. Jupiter's Great Red Spot is perhaps the most famous example of such a storm. It is an enormous anticyclonic storm, a persistent high-pressure region that has been continuously observed for over 350 years. It is so vast that 3 Earths could comfortably fit within its swirling boundaries. Its distinctive reddish-orange color is thought to come from complex organic molecules or phosphorus compounds that are brought up from deeper layers of Jupiter's atmosphere and then react with ultraviolet sunlight. The Great Red Spot is a testament to the longevity and power of these giant storms. Its edges are defined by powerful, counter-rotating jet streams that feed energy into the vortex, while its center is a relatively calm and warm region, a giant swirling eye in the heart of the tempest. Its shape and size do subtly shift over time, but its fundamental existence has endured for longer than human civilization has understood its nature. Saturn, another gas giant, also hosts its own unique atmospheric marvels. At its north pole, a striking and perfectly hexagonal storm system swirls with silent elegance. This hexagonal jet stream is unlike anything seen elsewhere in the solar system. Its 6 distinct sides are each approximately 13,800 kilometers or 8,600 miles long, wider than the Earth's diameter. The mechanism that maintains this stable and geometric shape is still a subject of active research, but it is thought to involve complex wave patterns in the deep and rapidly rotating atmosphere. These gas giant storms are dynamic environments in their own right. They are often accompanied by powerful lightning discharges, hundreds or even thousands of times more energetic than terrestrial lightning. They exhibit dramatic temperature gradients from their scorching depths to their frigid cloud tops, and their towering cloud structures can rise high above the surrounding atmosphere, like colossal cosmic mountains made of swirling gas. These long-lived tempests show us how profoundly different weather patterns can be on worlds where the fundamental rules of motion and heat transfer play out across scales that utterly dwarf our entire planet. They are silent and majestic examples of the universe's capacity for extraordinary and enduring phenomena, a slow and continuous dance of elemental forces. Entire galaxies, those vast and luminous cities of stars, sometimes form with so few stars that they appear almost empty. These are the ghostly galaxies, the dim and elusive members of the cosmic population. Astronomers, through painstaking and long observations, have discovered these faint systems. They are often little more than a scattering of stars, glowing faintly against the vast and overwhelming darkness of intergalactic space. These ethereal galaxies, these cosmic phantoms, may have begun their existence as ordinary concentrations of gas and dark matter, the typical ingredients for galaxy formation. However, various influences can severely stifle or even completely prevent their ability to create stars. One common scenario involves interactions with much larger and more massive neighboring galaxies. The powerful gravitational tides from these dominant companions can strip away the raw material, the precious gas, and dust that is so essential for new stellar births, leaving behind only thin and sparse remnants, a mere skeleton of a galaxy. In other cases, the early generations of stars within the nascent galaxy may have been exceptionally massive and short-lived. Their powerful stellar winds and their dramatic supernova explosions could have literally blown out much of the available gas from the galaxy's gravitational grasp, preventing later waves of star formation from ever occurring, leaving behind a galaxy that has prematurely exhausted its stellar nursery. What remains in these ghostly systems is a structure that is overwhelmingly dominated by dark matter. This invisible and mysterious substance exerts its gravitational pull, holding a fragile sprinkling of visible stars in place. These stars are like tiny jewels embedded in a vast and unseen halo of dark matter. Through long and patient observation and careful and meticulous analysis, researchers can trace how these sparse systems still faithfully follow the gravitational rules that govern much richer and more luminous galaxies. Their extreme dimness, paradoxically, helps to reveal the hidden architecture of cosmic evolution, showing us how environmental factors such as collisions and ancient events can profoundly shape a galaxy's destiny. Long before its stars grow plentiful or its light becomes bright. Even the very faintest of these stellar gatherings, these quiet and distant smudges, carries within it the intricate history of gravitational forces that acted upon it over billions of years. They are silent archives of the early universe, whispering stories of cosmic tides and lost opportunities for stellar growth, a gentle reminder of the diverse paths that galaxies can take through the cosmic ages. A stellar remnant, the quiet ghost of a once shining star, can shrink to the size of our Earth, while simultaneously becoming incredibly and impossibly dense. When certain stars, those of moderate mass, similar to our Sun, exhaust their nuclear fuel, their outer layers gently drift away into the vastness of space. They form expanding shells of gas that often create beautiful and ephemeral planetary nebulae. What is left behind is a compact core, a stellar cinder, that no longer generates energy through nuclear fusion. Without the outward push of those nuclear reactions, gravity, that persistent sculptor, begins to squeeze the remaining material inward. It compacts this stellar core into a volume that is surprisingly similar to the size of our own planet. However, the mass stored inside this small sphere can be comparable to that of our Sun. Imagine the Sun's mass packed into Earth's volume. This is a white dwarf star, a slowly cooling and fading ember of a once vibrant sun. Under these extraordinary pressures, the atoms within the white dwarf are forced into arrangements that simply cannot exist in ordinary conditions. The electrons are packed so tightly together that they behave collectively, forming a degenerate gas. This electron degeneracy pressure, a quantum mechanical effect, is what ultimately supports the white dwarf against further gravitational collapse. It is a force that arises from the fundamental laws of quantum mechanics rather than from thermal pressure. These stellar remnants, these silent embers, cool slowly over immense stretches of cosmic time. They patiently release their stored heat into the cold of space. Their faint glow and their unique spectral signatures allow astronomers to study the transition between active stars and the final states that await, many of them, including our own sun, billions of years from now. They also offer rare glimpses into the behavior of matter under conditions that challenge the very limits of physics, revealing insights that our terrestrial laboratories can never hope to match. White dwarfs are the quiet but profound laboratories of the cosmos, where fundamental forces are stretched to their ultimate breaking point. Planetary systems, those intricate and often orderly arrangements of worlds, occasionally develop, with planets orbiting at impossible-looking angles. Their paths are dramatically tilted out of the usual flat plane. As newborn systems slowly emerge from swirling clouds of gas and dust, they typically begin with disks that appear remarkably orderly and flat, like a cosmic frisbee or a spinning pancake. Planets usually form within this disk and therefore tend to orbit in roughly the same plane. However, over time, various gravitational influences can tilt or twist the orbits of smaller worlds. These influences might come from nearby stars making a close pass through the system, or from the subtle but cumulative tugs of other, more massive planets within the system itself. Or perhaps from a passing, rogue object, a stellar wanderer whose gravity perturbs the delicate dance. These interactions can be gentle and gradual, slowly nudging the orbital plane. Or they can be extremely violent, depending on the masses involved and the precise timing of the encounters. Once the orbital geometry begins to shift, resonances, those subtle but powerful gravitational feedbacks, can amplify the misalignments, sending planets onto paths that rise far above or drop far below the plane in which their neighbors travel. A cosmic ballet suddenly out of sync. Observations of exoplanetary systems, planets orbiting distant stars, have revealed worlds circling their stars along dramatic inclinations, paths that defy our old expectations about how planetary formation should proceed. These wildly tilted orbits are a testament to the dynamic and often chaotic history of these systems. Studying these unusual configurations helps scientists to understand the astonishing diversity of cosmic environments. It shows us how fragile the earliest stages of planetary development can be, and how even minor gravitational nudges can lead to profound and lasting changes. Each tilted orbit, each strangely angled path, offers clues about long-finished events. Ancient gravitational skirmishes that reshape the system in ways that are only now becoming visible to our patient gaze. They are silent histories written in the tilt of cosmic dance. Metal-rich asteroids, those rocky fragments drifting through space, can hold more precious material than the entire crust of our Earth. They are cosmic treasure troves, awaiting discovery. Scattered across our own solar system are countless fragments of ancient bodies, worlds that once experienced intense heating, melting, and a process called differentiation. In these early, primordial worlds, heavy elements like iron and nickel sank toward the center, forming dense metallic cores. Much like Earth's core, but on a smaller scale. Long ago, catastrophic collisions shattered some of these differentiated objects, sending pieces of their metallic cores drifting through space. When we detect these fragments today, in the form of asteroids, we find bodies composed of nearly solid metal, often buried beneath thin layers of dust or silicate rock. These are the so-called EMP-type asteroids or metallic asteroids. Their interiors can contain concentrations of valuable elements far, far higher than anything found naturally on our planet's surface. Beyond just iron and nickel, they may harbor significant amounts of platinum group metals, such as platinum, palladium, and rhodium, as well as gold and other rare elements that are much scarcer in Earth's crust because they sank to our own planet's core during its formation. By studying their spectra, the unique light they reflect, and their densities, scientists learn not only about potential future resource opportunities for humanity, but also about the violent and dynamic history of planetary formation. These metal-rich remnants preserve the internal structure of primordial worlds, offering a direct window into the processes that shaped the earliest solid bodies in our solar system, long before planets settled into stable orbits and oceans of molten rock slowly cooled into solid crusts. They are silent witnesses to the fiery birth of worlds. Massive stars, those colossal and brilliant giants, burn through their nuclear fuel so quickly that their lives end in what amounts to a mere instant when compared to the vast and sweeping timescales of the cosmos. Although these colossal stars possess far more hydrogen and helium than ordinary suns like our own, they consume their supplies at truly astonishing rates. Their cores burn fiercely, generating staggering amounts of energy that stream outward as intense light and searing heat. This powerful radiation pushes outward with such incredible force that the stars must constantly balance their own immense brilliance against the relentless inward pull of gravity. The more massive the star, the more violent and precarious this struggle between outward pressure and inward gravity becomes. Over relatively short spans of millions of years, the intense pressure and temperature in their cores forces the star to fuse heavier and heavier elements, progressing rapidly from hydrogen to helium to carbon, oxygen, neon, magnesium, silicon, and finally to iron. Each stage burning faster and hotter than the last, pushing the star toward an inevitable and dramatic collapse. While a smaller star, like our Sun, may shine for billions of years, these cosmic giants blaze through their existence in spans that on cosmic scales are closer to fleeting moments. Their lives are short but spectacularly brilliant. When they reach the very end, their deaths unfold in spectacular ways that profoundly reshape the surrounding space. The heavy elements forged in their superheated cores during their lives, and especially during their final, explosive moments, are then scattered outward. They enrich the environments where future generations of stars and planets will eventually form. These elements are the very ingredients for rocky worlds and for the complex chemistry of life itself, a silent and fiery cycle of cosmic recycling where the death of one star sows the seeds for countless new beginnings. Some planets, those iridescent jewels in the cosmic night, reflect so much starlight that they appear to shine like tiny suns. They are beacons in the deep dark, glowing with borrowed light. Their remarkably bright and luminous appearance comes from highly reflective cloud decks in their atmospheres, or from surfaces composed of materials that scatter incoming radiation. With remarkable and exceptional efficiency, these worlds may orbit very close to their host stars, receiving intense illumination that bathes their atmospheres or their terrains in continuous and brilliant brightness. The precise chemical composition of their clouds or their icy surface layers profoundly shapes the way light bounces from them, creating a brilliance that can rival the luminosity of much larger objects, even some smaller stars. For instance, some exoplanets, known as hot Jupiters, orbit so close to their stars that their atmospheres are incredibly hot. Minerals like silicates or even titanium oxide can vaporize into fine particles, forming shimmering layers of cloud that intensify their reflective glow. Astronomers studying these planets can detect their reflected light, even when the planets themselves cannot be directly imaged. This indirect detection reveals crucial details about their atmospheres, their chemical makeup, and their orbital dynamics. Their luminous appearance helps researchers to explore how different temperatures, pressures, and chemical mixtures influence a planet's ability to reflect radiation. These bright worlds are silent laboratories for understanding the diversity of planetary atmospheres. They show us the extraordinary and unexpected ways that planets can interact with the powerful light of their parent stars. Each shimmering reflection is a whisper about the hidden chemistry of distant skies. Certain regions of space contain magnetic fields millions of times stronger than Earth's. These are zones of invisible power shaping the cosmic ballet of charged particles. These immensely powerful fields emerge near compact remnants, such as neutron stars and black holes, or within dense clusters of galaxies, or in environments where charged particles move through concentrated gravitational landscapes. When vast amounts of material, gas and dust, spiral inward toward a collapsed object, like a black hole, it can generate powerful electric currents. These currents, in turn, intensify the surrounding magnetism, creating an invisible structure of immense strength. The result is a cosmic architecture that guides particles along tight and precise paths, accelerating them to extraordinary and relativistic energies. These strong magnetic zones profoundly shape the behavior of gas, dust, and radiation, influencing everything from the formation of powerful jets that erupt from galactic centers to the emission of intense bursts of light from magnetars. In some extreme cases, the magnetic fields become so dominant, so overwhelmingly powerful, that they can literally deform atoms, stretching them into unusual shapes not found in familiar conditions here on Earth. This is a testament to the truly extreme physics at play. By studying the light from these environments, astronomers can trace how magnetic forces affect matter under pressures and temperatures that simply cannot be reproduced in any laboratory on Earth. These findings deepen our understanding of the fundamental physics that governs some of the most extreme regions of the universe. They are silent but powerful demonstrations of forces that transcend our everyday experience. Galaxy clusters, those immense and luminous gatherings of hundreds or even thousands of galaxies, can bend and subtly stretch the faint and ancient starlight from objects far, far beyond them, creating graceful and luminous arcs across the cosmic canvas. The immense mass contained within these colossal clusters, which includes not only the visible galaxies, but also vast amounts of hot, intergalactic gas, and the invisible but gravitationally dominant dark matter, creates gravitational fields. Fields so incredibly strong that they can profoundly distort the paths of photons of light traveling through them. As light from remote galaxies located far behind the cluster passes near, these concentrations of mass, space itself, the very fabric of space-time, curves. This curvature acts like a colossal lens, guiding the light rays into new trajectories, a phenomenon known as gravitational lensing. When the alignment between the distant galaxy, the foreground cluster lens, and our observatories here on Earth is just right, the background galaxy can appear warped or dramatically magnified. Its image can be stretched into long and elegant arcs. Or, if the alignment is almost perfect, it can form complete or partial luminous rings, known as Einstein rings. In some cases, multiple images of the same distant galaxy can even be seen scattered around the cluster. These fascinating distortions, these subtle shifts in the appearance of faraway light, are incredibly valuable. They reveal the intricate distribution of both visible matter, like stars and gas, and the unseen, enigmatic dark matter within the cluster. Observing these patterns, these cosmic optical illusions, allows researchers to map the hidden structures of dark matter, material that emits no light of its own and cannot be seen directly. The faint and stretched shapes of these lensed galaxies provide a natural cosmic telescope, a phenomenon that can amplify objects that are simply too distant or too faint to study directly with our conventional telescopes. It is like using a magnifying glass, the size of an entire cluster, to peer into the earliest moments of the universe. Each distorted image, each luminous arc, carries crucial clues about the expansion of the universe itself, about the growth of large-scale structures like galaxy clusters over billions of years, and about the mysterious components like dark matter that profoundly shape the vast and intricate cosmic web. These gravitational lenses are silent windows into the universe's deepest past and its invisible architecture. Dying stars, those aging and transforming celestial bodies, sometimes release their outer layers of gas in complex and intricate shapes, forms that appear almost as if they were sculpted by some unseen cosmic hand. As these stars reach the very end of their long lives and exhaust their nuclear fuel, their outer layers begin to loosen and drift away into the surrounding space. This process is often not a simple or uniform expansion. Instead, gentle pulses of energy from the star's interior can lift distinct shells of gas outward. Later, faster winds of charged particles follow behind, catching and reshaping the earlier material, creating a dynamic and ever-changing interaction. The resulting structures are often breathtaking in their beauty and complexity. They can form perfectly symmetrical rings, or elegant hourglass shapes, or delicate and intricate filaments that twist and weave through space in patterns that defy simple explanation. These are known as planetary nebulae, a misnomer from early observations, when they appeared like faint, round planets through small telescopes. The vibrant colors that we observe in these nebulae arise from different elements glowing in response to the star's fading, but still intense heat. Hydrogen, for instance, often glows with a deep red hue. Oxygen can emit a striking blue-green light, and nitrogen might appear as a subtle yellow. Each element a brushstroke in the cosmic masterpiece. Over time, the central remnant, the white dwarf that is left behind, slowly cools and dims, while the expanding gas of the nebula continues to spread into the vast and diffuse interstellar environment. Eventually, after tens of thousands of years, the gas becomes so thin and so dispersed that it fades into the background of interstellar space, becoming invisible to our telescopes. Each unique and intricate structure of a planetary nebula reflects the star's internal rhythms, its rotational speed, and the influence of its magnetic fields. During its last active phases, if the star had a close companion in a binary system, the interaction between the two stars could also profoundly shape the nebula's morphology, creating even more complex and asymmetrical forms. These beautiful forms, these cosmic sculptures, show us the dramatic transformations that unfold when stars reach the very ends of their lives, and how they contribute their enriched material back into the vast reservoir of the galaxy, providing the heavy elements that will form future generations of stars and planets. They are silent and colorful testaments to stellar recycling. Star-forming clouds, those colossal and often dark reservoirs of gas and dust, can collapse under their own immense gravity, giving rise to entire families of new suns, a quiet but powerful act of cosmic creation. Across the galaxy, immense clouds of hydrogen gas and fine dust particles drift in relative darkness for long periods. They are cold and diffuse, seemingly quiescent, until some disturbance unsettles their calm equilibrium. This disturbance might be a passing shockwave from a nearby supernova explosion, or the subtle but persistent pull of a nearby cluster of stars. Or perhaps the influence of an earlier generation of massive stars whose powerful winds compressed the gas. Whatever the trigger, it causes subtle ripples or localized increases in the density of the cloud. Once a region within the cloud becomes sufficiently dense, gravity, that relentless sculptor, begins to draw its material inward. The process of gravitational collapse has begun. As the collapse accelerates, the vast cloud does not simply shrink as a whole. Instead, it fragments into multiple, smaller pockets or cores. Each one of these pockets gradually grows hotter and denser at its center. This is where the new stars will eventually be born. Within these pockets, pressure rises as the material becomes more and more compressed, until the material begins to glow with the gentle warmth of a forming protostar. It is not yet a true star fusing hydrogen, but it is a nascent sun slowly gathering its strength. Surrounding each glowing center, the leftover gas and dust settles into swirling disks. These protoplanetary disks are crucial. They shape the flow of matter onto the growing protostar, and they set the stage for worlds, planets, and moons yet to come to coalesce from the swirling debris. Over time, an entire group, a family, of newborn suns emerges from the same collapsing structure. Some are massive and brilliant, destined for short but spectacular lives. Others are small and dim, destined for long and quiet existences. And many may even become companions orbiting together in binary or multiple star systems. These families of stars, these open clusters, carry a shared origin. Their early histories are written in their precise motions and their identical chemical compositions. Long after the original cloud of gas and dust has dispersed and vanished, these stellar siblings continue their journey through the galaxy, a silent testament to their common birth. Planetary orbits, those precise and often elegant paths that worlds follow around their stars, can evolve into strange and elongated shapes after powerful gravitational encounters. A cosmic dance with unexpected turns. When planets share a system with massive neighbors, their paths around the central star can be subtly but profoundly influenced by gravitational interactions. These interactions unfold over long stretches of cosmic time. A close passage between two worlds, for instance, might gently nudge one of them outward, increasing the eccentricity of its orbit, making it more elliptical and less circular, until it resembles a stretched ellipse instead of a nearly perfect and stable circle. Additional tugs from other bodies within the system, or even from distant, passing stars, can further exaggerate this effect, turning a once stable path into something far more extreme. A planet might swing perilously close to its star at one point in its orbit, and then journey far out into colder and darker regions at another. Such dramatic variation in orbital distance can profoundly reshape the planet's climate, altering its atmospheric chemistry and driving intense geological processes. A world might experience cycles of extreme heating and then deep freezing as it travels along its elongated path. Even minor encounters over billions of years can accumulate, gradually shifting orbits into configurations that defy our initial expectations. Observations of distant systems, exoplanetary architectures, reveal worlds moving in ways that strongly suggest long histories of gravitational shaping. Some planets are found on highly eccentric orbits, swinging in close and then far out, while others are locked in complex and unstable resonances with their neighbors. Each distorted orbit, each strangely elongated path, tells a silent story of past interactions, of hidden events that took place eons ago, and of the invisible but powerful architecture of forces that sculpt the evolution of entire planetary families. These orbits are cosmic fingerprints of a system's tumultuous past. Black hole jets, those colossal and blazing streams of particles, can shoot across distances larger than their host galaxies. They are cosmic geysers of unimaginable power. Near the centers of certain galaxies, particularly those that are active and rapidly growing, swirling disks of superheated material, gas, and dust spiral relentlessly inward. They are drawn ever closer to a compact object at the very heart of the galaxy, a supermassive black hole whose gravitational pull is so intense that nothing, not even light, crossing its inner boundary, the event horizon, can ever hope to escape. However, before material reaches that final point of no return, powerful magnetic forces and the rapid rotation of the black hole and its accretion disk can channel a significant portion of this infalling matter upward and downward along tightly focused axes perpendicular to the disk. These channels become the launch sites for incredibly powerful and collimated streams of charged particles. These particles are accelerated to speeds that approach the very limit of the speed of light. Once unleashed, these jets pierce through the surrounding gas and continue outward for truly vast distances. Some of these jets extend far beyond the visible structure of the galaxy itself, carving narrow paths through the diffuse and almost empty intergalactic space. Along their immense journeys, they illuminate previously dark clouds, ignite powerful shock fronts, and heat clusters of material that might otherwise remain cold and unseen. They are invisible searchlights, revealing the cosmic web. Their presence is a powerful revelation of the immense energy hidden within these compact remnants, and it shows how these objects, supermassive black holes, can influence environments far larger than themselves. They are not merely gravitational sinks, but also cosmic engines of immense power. The jets serve as beacons, tracing the flow of energy from regions where gravity dominates all other forces. They are silent and blazing testaments to the extreme physics at the heart of galactic evolution, a profound connection between the smallest and most powerful of cosmic engines and the largest structures in the universe. Some moons, those silent companions to giant planets, experience tidal heating, a warmth generated from within, strong enough to melt rock deep underground. As these moons travel around their massive parent planets, they often follow slightly oval orbits rather than perfect circles. These elliptical paths carry them closer to the planet during one part of the orbital cycle, and then farther away during another. This changing distance causes subtle but persistent shifts in the gravitational pull exerted by the planet, stretching and compressing the Moon repeatedly with each orbit. This continual flexing and internal straining generates friction deep within the Moon's interior, warming layers of rock and ice that would otherwise remain perpetually frozen. Over time, that warmth, that internal heat, can accumulate until pockets of material deep beneath the surface begin to melt, forming reservoirs of liquid far beneath the icy and rocky crust. In some cases, this immense heat drives plumes of water vapor or icy particles. These plumes erupt through cracks and fissures in the surface, sending material into space. Enceladus, a moon of Saturn, is a prime example, with its geysers of water vapor and ice particles erupting from its south pole. These plumes are direct evidence of a subsurface ocean beneath its icy shell. In other cases, the heat fuels slow circulation within subsurface oceans that remain hidden under thick crusts of ice. Europa, a moon of Jupiter, is believed to harbor such a vast, salty ocean deep beneath its cracked and icy exterior. Its surface shows evidence of recent geological activity, suggesting an active interior. These internal processes, these silent and powerful forces, reshape landscapes from within and can create environments where complex chemical reactions can flourish. Despite the extreme cold, on the surface, the heat produced by these tides demonstrates how the motion of a moon through the gravitational fields of its parent planet can transform its interior far beyond what sunlight alone could ever achieve. They are silent and profound testaments to the hidden power of gravity. Ancient starlight, that faint and timeless glow, can travel across the cosmos for billions of years before it finally reaches our gentle Earth. Each photon a messenger from a distant past. When a distant star or an entire galaxy emits light, that light begins an immense journey through the expanding and ever-changing fabric of the universe. Along the way, it passes through regions filled with clusters of galaxies, with vast filaments of intergalactic gas and with enormous empty voids. These cosmic structures can stretch or subtly shift the light's color, a phenomenon known as cosmological redshift. Some wavelengths of this ancient light are absorbed by intervening gas clouds, leaving telltale spectral lines that reveal their composition, while others continue uninterrupted their tireless journey until they finally reach our telescopes here on Earth. Because the universe is so unimaginably vast and constantly expanding, the distance these photons travel is truly immense. By the time they arrive at our detectors, the sources that originally emitted them may have changed dramatically or even ceased to exist billions of years ago. The light, therefore, becomes a precious record, a cosmic photograph of how those objects looked eons ago, frozen in time and preserved within its wavelength and intensity. Scientists use these ancient signals to reconstruct the early eras of cosmic evolution, to peer back through time and see structures as they appeared when the universe was young and very different. Each photon carries information about its birthplace, its journey, and the conditions of the universe at the moment it was emitted, creating a vast and intricate timeline of events that would otherwise remain forever hidden from our view. These ancient lights are whispers from the dawn of time. Dust-filled nebulae, those dark and often mysterious clouds of cosmic dust, can effectively hide fully formed stars behind thick veils of shadow. They are cosmic cloaks concealing stellar secrets. Within certain regions of space, clouds of fine particles, tiny grains of silicate and carbonaceous dust gather so densely that they completely block visible light from passing through. These dark nebulae appear as stark silhouettes against brighter backgrounds, masking whatever lies inside their opaque depths. They are often called dark clouds or molecular clouds because they are cold and dense enough for atoms to combine into molecules. Though the dust effectively obscures our view in visible light, infrared observations reveal that many of these regions are far from empty. They contain stars already glowing with the gentle warmth of their nascent fusion. The dust grains absorb and scatter visible wavelengths, but longer wavelengths of infrared light slip through more easily, allowing astronomers to peer into the concealed interiors of these stellar nurseries. Inside, newborn stars patiently gather material from the surrounding gas and dust. They are often surrounded by swirling disks of leftover material, the protoplanetary disks that may eventually give rise to planets. The same dust that hides them plays a vital role in cooling the cloud and enabling the gravitational collapse to continue. Without this cooling, the gas pressure would resist the inward pull of gravity. As the stars grow stronger and more luminous, their intense radiation and powerful stellar winds eventually disperse the surrounding fog of dust and gas, revealing the clusters of young stars that spent millions of years concealed within the darkness. The interplay between darkness and hidden light makes these nebulae essential laboratories for understanding how stars evolve from infancy to visibility. They are silent and profound stages for the birth of suns. Violent stellar winds, those powerful and relentless streams of charged particles, can strip atmospheres away from vulnerable planets, leaving them exposed to the harsh and unforgiving cosmic environment. When massive or highly active stars emit streams of charged particles at incredibly high speeds, these stellar winds sweep outward, filling the surrounding space with energetic flows. A planet orbiting close to such a star may find its upper atmosphere battered and eroded by this continuous and relentless onslaught. Over time, the energetic particles within the stellar wind can collide with atoms in the planet's atmosphere, heating them and imparting enough energy for them to escape into space. This process, known as atmospheric escape, can be particularly efficient for lighter gases like hydrogen and helium. Planets without strong global magnetic fields are particularly at risk. This is because they lack the protective shield that a magnetosphere can provide. A magnetosphere can deflect or channel the incoming stellar wind away from the planet's atmosphere. Mars, in our own solar system, is thought to have lost much of its early atmosphere due to this process, after its magnetic field weakened billions of years ago. As the atmosphere gradually thins, the planet's surface becomes more exposed to the damaging effects of stellar radiation and to extreme temperature swings between day and night. In some cases, such atmospheric erosion may transform a once temperate world, a potentially habitable planet, into a barren and lifeless landscape, a silent transformation from potential to desolation. By studying the intricate interactions between stellar winds and planetary atmospheres, scientists can evaluate which worlds may remain stable and potentially habitable over long periods, and which face long-term depletion of their vital atmospheric gases. These insights are crucial in shaping the ongoing search for environments beyond Earth that might support life. They are silent warnings from the cosmic winds. High-energy radiation from massive stars can sculpt nearby clouds of gas and dust into towering pillars. These majestic and ethereal structures are cosmic monuments to stellar power. When young giants, those incredibly massive and luminous stars, ignite within a dense region of gas and dust, they release intense ultraviolet light. This powerful radiation streams outward in all directions like a cosmic floodlight. This radiation ionizes the surrounding material, stripping electrons from atoms and heating the gas. It also exerts a pressure, a subtle push, against the cloud, driving shock fronts that reshape its delicate structure. Less dense areas within the cloud evaporate quickly under the relentless onslaught of radiation, while regions with slightly higher density resist this erosion. They act like natural shields, protecting the material behind them. Over time, these resistant clumps become elongated structures. As the surrounding gas is stripped away, they form tall columns and majestic ridges that point back toward the energetic sources, the massive stars that sculpted them. These are often called pillars of creation or elephant trunks, due to their evocative shapes. Within the protected interiors of these pillars, shielded from the harsh and destructive radiation, gravity can continue to act, allowing new stars to form in relative safety. These pillars are thus regions of both destruction and creation simultaneously. Observations of these structures in stellar nurseries like the Eagle Nebula reveal dynamic environments where creation and destruction unfold side by side. The pillars stand as silent monuments to the immense power of massive stars and the remarkable resilience of the raw material from which future generations of stars may eventually emerge. They are cosmic cathedrals carved by light. Magnetic fields in the vast emptiness of space can twist and confine blazing streams of charged particles. These invisible forces sculpt the cosmic plasma into luminous and intricate forms. Across galaxies, charged particles, such as electrons and protons, move through environments that are profoundly shaped by invisible magnetic structures. These fields arise from the motion of electrically conductive gas or plasma, from the rapid rotation of stars and planets, and from the complex dynamics of compact remnants like neutron stars and black holes. Once established, these magnetic fields create invisible pathways. They act like cosmic highways that guide the movement of electrons and ions. Charged particles do not travel in straight lines through these fields. Instead, they spiral along the magnetic lines like beads on an invisible string, often traveling great distances while emitting radiation that reveals their presence to our telescopes. The strength and orientation of these fields vary from place to place across the cosmos, shaping the behavior of cosmic rays and affecting the intricate structure of nebulae and the powerful jets that erupt from active galactic nuclei. In regions with complex and turbulent magnetic activity, particles can become trapped in magnetic loops or channeled into narrow beams that stretch far from their origins, creating luminous arcs and filaments that trace the invisible architecture of these fields. By carefully examining the shapes and intensities of these structures, astronomers can infer the strength and orientation of the underlying magnetic fields. The behavior of these trapped particles reveals how magnetic forces influence energy distribution, star formation processes, and the long-term evolution of cosmic structures. These interactions provide us with invaluable insight into processes that remain difficult or even impossible to replicate in terrestrial laboratories. The influence of magnetic fields demonstrates how even unseen forces contribute to the dynamic and ever-changing nature of the universe. They are silent and powerful sculptors of the cosmic plasma. Planetary collisions, those violent and catastrophic encounters, can reshape entire worlds in a single, dramatic moment. They are the scars and the catalysts of planetary evolution. During the chaotic, early stages of a system's formation, countless solid bodies, from tiny planetesimals to nascent protoplanets, move along intersecting paths. It is a cosmic demolition derby, where worlds are forged and broken, when two sizable objects meet at incredibly high speeds. The resulting impact can alter their structures in dramatic and profound ways. Mountains can melt in an instant, vaporizing into vast plumes of superheated rock. Oceans can boil away into space, and crusts can be shattered into countless fragments, releasing immense amounts of internal heat. Some collisions are gentle enough to merge the two bodies into a single, larger world, adding to its mass and reshaping its interior. Others are so violent that they tear the colliding bodies apart, scattering fragments across the system. These fragments may later reassemble under gravity to form new moons or rings or smaller companion bodies. Our own moon is thought to have formed from such a giant impact between the early Earth and a Mars-sized body billions of years ago. The immense heat generated by such impacts can create global magma oceans, resetting a planet's surface entirely, erasing any previous geological history. Evidence of ancient collisions is preserved in the heavily cratered landscapes of many moons and planets in our solar system, in the unusual rotations and tilts of planetary axes, and in the unexpected compositions of certain worlds. For instance, the unusual density of Mercury is thought to be due to a giant impact that stripped away much of its silicate mantle. By studying these scars, these cosmic fingerprints, researchers can reconstruct the violent histories that shaped the planets we see today. Each collision leaves an indelible imprint, a silent record that reveals how even stable-looking worlds are the products of intense and transformative events. They are silent and powerful reminders of the universe's creative destruction. Rings, those ethereal and majestic structures that encircle distant planets, can stretch wider than the entire distance between our Earth and its moon. They are cosmic halos of icy beauty. These enormous structures form when material such as dust, ice, and fragments of rock becomes trapped in orbit around a planet, rather than coalescing into a single, larger moon. This material circles in countless individual paths, each grain responding to the planet's gravity and to tiny, gentle collisions with its neighbors. The brightness and the intricate texture of a ring system depend crucially on the size and composition of its constituent particles. Some rings shine softly with fine, icy grains that brilliantly scatter starlight, creating a luminous and diffuse glow, while others contain darker fragments of rock and dust that absorb more light and therefore appear faint even when they span incredible distances. In young planetary systems, collisions between forming moons or between planetesimals can produce fresh debris. This material then spreads into broad arcs and temporary rings. Over time, gravitational interactions with moons or with the planet itself can carve the rings into narrow bands, distinct gaps, and delicate waves, creating patterns that shift gradually as the orbits of the particles and the moons evolve. Saturn's rings are the most famous example in our solar system. They are composed almost entirely of water ice particles ranging in size from micrometers to tens of meters. The intricate structure of Saturn's rings, with its numerous divisions and ringlets, is shaped by the gravitational influence of its many moons. Some small moons, known as shepherd moons, orbit within or near the rings, using their gravity to keep the ring particles confined into narrow bands. When astronomers observe rings around distant worlds, they see more than just beautiful structures. They see direct evidence of ancient impacts of migrating moons and of the subtle forces that shape entire planetary systems. These vast rings show us how dynamic and varied worlds can be, even when they lie far from the warmth and light of their central stars. They are silent and glittering records of cosmic history. Some stars orbit each other so incredibly closely that they actually share their outer layers of gas. They are cosmic dancers entwined in a gravitational embrace. In these extraordinary binary systems, two stars form so near to each other that their powerful gravitational fields overlap, creating a common envelope of gas. As they evolve, one of the stars, which is often the more massive one, may expand into a swollen giant as it runs out of hydrogen fuel in its core. Its outer layers then begin to spill over across a gravitational boundary known as the Roche lobe towards its companion star. The flowing material, this stellar transfer, forms a bridge of glowing gas suspended between the two bodies, creating a swirling region, an accretion disk, where gas circulates under the combined tug of both stars. This exchange of mass, this cosmic transfusion, can dramatically alter the fates and evolutionary paths of both stars. The receiving star, the one accumulating gas, gains mass and therefore grows hotter and brighter. Its life cycle is effectively rejuvenated or extended by this influx of fresh fuel. Meanwhile, the losing star, the donor, becomes stripped of its outer layers. This process can reveal deeper layers of its interior that would normally remain hidden beneath the surface, exposing elements that tell a tale of its inner workings. The shared atmosphere. This common envelope can generate complex patterns of heat and motion, leading to powerful eruptions, intense flares, or regular pulses of radiation that vary over precise and predictable intervals. These binary systems are often variable stars whose brightness changes over time due to the mass transfer. Observing these systems gives astronomers a unique and invaluable view of stellar evolution, because the stars influence one another in ways that solitary stars never experience. They are cosmic laboratories where stellar lives are intertwined and profoundly altered. Their intertwined lives demonstrate how companionship in the cosmos can produce outcomes far more dramatic and complex than either star could ever achieve alone. These close binary systems are not just two stars, but a single dynamic entity evolving together in a cosmic dance of mutual influence. Dense globular clusters, those ancient and glittering spheres of starlight, can pack hundreds of thousands of stars into remarkably tight and compact volumes. They are cosmic cities brimming with ancient suns. These ancient collections of stars orbit the outskirts of galaxies like luminous beacons of stellar history. Each cluster contains stars that formed at nearly the same time from the same primordial cloud, making them some of the oldest and most well-preserved surviving structures in the universe. They are true fossils of the early cosmos. Because they are so incredibly densely packed, the stars within them lie far closer together than the stars in typical regions of a galaxy. Imagine our Sun having hundreds or thousands of stellar neighbors within a few light years. In such crowded conditions, gravitational encounters between stars are frequent and often dramatic. These encounters can fling stars outward from the cluster into the galactic halo. They can draw others inward toward the cluster's core, and they can profoundly alter the orbits of many stars, creating a constantly shifting and dynamic internal environment. It's a cosmic dance where every step is influenced by every other. Some of the stars found in globular clusters are unusually blue and remarkably bright. These are often called blue stragglers. They appear younger and more massive than the other stars in the cluster, despite having formed at the same time. They are thought to have formed through mergers of two smaller stars or through mass transfer events between close binary companions. These events are triggered by the frequent and close interactions in the crowded cluster core. The clusters maintain their tight shapes, their spherical symmetry, because their combined mass, the collective gravity of hundreds of thousands of stars, keeps the individual stars bound together, despite the constant motion and internal dynamics. They are self-sustaining gravitational islands. Studying them reveals how early star formation unfolded in the universe, and how nature has managed to preserve these ancient spheres across the immense stretches of cosmic time. Globular clusters are silent and glittering archives of the universe's stellar beginnings. The interstellar medium, that vast and diffuse sea of gas and dust between the stars, can carry powerful shock waves from ancient supernova explosions. These are cosmic ripples carrying echoes of stellar death. When a star, many times more massive than our Sun, explodes in a spectacular supernova, the blast sends out a powerful front of energy and superheated material. This shock wave sweeps through the surrounding space, expanding outward at tremendous speeds. Although the interstellar medium appears thin and largely empty, it contains gas, dust, and charged particles. These components can be pushed and compressed by these relentless waves. As the shock wave travels onward, it heats the material it encounters. This heating can sometimes trigger new chemical reactions in the gas, or excite atoms, causing them to glow in characteristic colors that can be observed through telescopes. These glowing regions are often called supernova remnants. These waves can continue expanding for millions of years across vast distances, shaping the structure of nearby molecular clouds and profoundly influencing the birth of new stars. The effects ripple outward across immense distances, leaving behind shells and vast bubbles of expanding gas, or delicate filaments that mark the path of the ancient explosion. By examining these patterns, these cosmic fingerprints, astronomers can estimate when the original supernovae occurred and how much energy it released into the interstellar medium. Each shock wave becomes a messenger from a long-vanished star, carrying information across space. In the subtle changes it imprints on the interstellar medium, they are silent and powerful echoes of cosmic destruction that can spark new creation. Some planets, those extraordinary worlds, orbit so rapidly around their stars that their years last only a few Earth days. They are cosmic speedsters, locked in a dizzying dance. These worlds circle their stars at such close range that gravity pulls them along dizzying paths. With each swift orbit, they experience intense radiation and dramatic temperature swings. Their surfaces, or atmospheres, face challenges that no planet in our own gentle solar system ever encounters. On the star-facing side, the perpetual day side, heat can build to levels that melt rock or vaporize minerals, creating seas of molten lava or clouds of metallic vapor. On the far side, the perpetual night side, temperatures can plunge sharply to extreme cold unless powerful winds efficiently distribute the heat from the day side. The quick pace of each orbit creates unique atmospheric patterns, as currents struggle to keep up with the rapid cycle of scorching day and frigid night. Some of these planets are tidally locked, so that one side always faces the star, like our moon facing Earth, intensifying the contrast between blinding light and deep, unending darkness. By studying these extreme environments, scientists learn how planets respond to conditions far beyond those found on Earth. Their short years and blistering climates expand our understanding of what worlds can become. They are silent and dramatic testaments to the universe's astonishing diversity of planetary environments. Spiral galaxies, those elegant and graceful pinwheels of stars, can grow new arms as they interact with neighboring systems. They are cosmic dancers, reshaping each other through gravitational tugs. The graceful spirals that define these galaxies may appear stable and serene, yet their intricate shapes are profoundly influenced by gravitational forces from surrounding objects. When another galaxy passes nearby, even without direct physical contact, its gravitational pull can disturb the delicate distribution of stars and gas in the spiral galaxy's disk. Waves of density can propagate through the disk, much like a traffic jam on a highway. These waves compress material into arcs that gradually curve into new spiral arms. These arms are not rigid structures composed of the same stars moving together, but rather they are patterns where stars and gas bunch together for a time before drifting onward. Gas within these arms becomes denser. This compression encourages the formation of bright, young stars and star clusters. These luminous, newborn stars enhance the spiral appearance, making the arms stand out against the dimmer background. Over millions of years, repeated interactions with neighboring galaxies can reshape the entire structure of the host galaxy. In some cases, new arms emerge while older ones fade or twist into distorted loops. Observations of such transformations reveal how galaxies evolve through these gravitational encounters, and how the cosmic environment, the presence and motion of other galaxies, influences their long-term development. They are silent and slow motion bullets of cosmic reshaping. Massive star clusters, those brilliant and densely packed gatherings of young stars, can light up the surrounding gas with intense ultraviolet radiation. They are cosmic floodlights, illuminating their birthplaces. Clusters containing many hot and exceptionally luminous young stars produce significant amounts of high-energy light, primarily in the ultraviolet part of the spectrum. This radiation streams outward in all directions, filling the surrounding space. When this intense radiation meets nearby clouds of hydrogen-rich gas, it strips electrons from the atoms, a process known as photoionization, and heats the cloud. The gas then glows with a distinctive set of vibrant colors. These emission lines reveal its chemical composition and its temperature. The surrounding region becomes a bright nebula, a luminous cloud with tendrils and intricate shapes carved out by the powerful forces at play. The famous Orion Nebula is a prime example of such a region, brilliantly illuminated by the young and massive stars of the trapezium cluster at its heart. Winds from the powerful stars push the gas outward, while the radiation sculpts the cloud into pillars, ridges, and vast cavities. Over time, as the cluster evolves, the brightest and most massive stars burn out quickly in supernova explosions, leaving behind a changing landscape of light and shadow. These illuminated regions, these glowing nebulae, help astronomers to trace how star formation progresses within clusters, and how young stellar communities profoundly influence their immediate environments. The sheer brilliance of these regions showcases the immense power that even a single cluster can exert on the cosmic neighborhood around it. They are silent and colorful testaments to the transformative power of young stars. Rogue stars, those solitary wanderers of the cosmos, can travel at immense speeds through the cold and empty reaches of intergalactic space. They are cosmic exiles speeding through the void. These solitary travelers are thought to have been flung out of their home galaxies by powerful gravitational encounters that imparted incredible momentum to them. Some may have passed too close to a supermassive black hole at the center of their galaxy, receiving a gravitational slingshot that propelled them to escape velocity, while others were ejected during complex interactions among multiple massive stars. In crowded star clusters, once expelled and truly free, they race through space with no galaxy to call home. Their paths take them into regions where starlight is incredibly faint and matter is exceedingly sparse, making them difficult to detect and even more challenging to study. However, their speeds and their precise trajectories reveal clues about the violent events that launched them. By carefully measuring their motion, astronomers can trace back to the dramatic moments that set them free, to the gravitational skirmishes that propelled them on their solitary journeys. Though isolated, these rogue stars carry with them the chemical signatures of their origins. The elemental composition of their atmospheres provides insight into the environments from which they came, whether they were born in a rich spiral arm or an ancient globular cluster. Their journeys remind us that even stars, those seemingly stable and eternal beacons, can experience dramatic displacements, events that send them wandering across the great emptiness between galaxies. They are silent and swift messengers from the dynamic and often violent heart of the cosmos. Some planetary systems, those intricate and diverse architectures of worlds, form multiple asteroid belts, structures that resemble cosmic rings encircling their stars. During the early stages of planetary formation, leftover material from the birth of planets often remains in stable orbits around the central star. These belts consist of countless rocky fragments ranging in size from tiny grains of dust to substantial bodies tens or hundreds of kilometers across. Over time, gravitational influences from the newly formed planets sculpt the belts into separated regions rather than continuous fields of debris. The gaps between the belts form where gravitational resonances disrupt the orbits of the smaller bodies, clearing paths that remain empty or sparsely populated. Much like Jupiter's gravity creates the Kirkwood gaps in our own asteroid belt, each belt reflects the unique history of its system, showing how collisions, planetary migrations, and gravitational shaping have distributed the leftover debris. The presence of multiple belts suggests a complex past with intricate interactions that influenced how planets settled into their current positions, and how the entire system evolved over billions of years. Observing these structures in distant systems, exoplanetary debris disks, allows astronomers to compare them with familiar features in our own solar system, like the main asteroid belt between Mars and Jupiter, and the Kuiper belt beyond Neptune, which is home to icy bodies. These comparisons deepen our understanding of how planetary systems evolve, and how debris patterns reflect their early history and the processes of planet formation. These cosmic rings are silent archives of a system's tumultuous youth. Quasars, those astonishing and incredibly luminous objects, can shine with the power of trillions of stars combined. They are cosmic beacons blazing from the dawn of the universe. These extraordinary objects reside in the hearts of young and active galaxies, where vast amounts of gas and dust spiral relentlessly inward toward supermassive black holes. As the material falls inward, it forms a massive and rapidly rotating disk known as an accretion disk. This disk heats to extreme temperatures from friction and compression. The disk then radiates across the entire electromagnetic spectrum, producing enormous luminosity that can utterly outshine the entire host galaxy. Surrounding clouds of gas absorb and re-emit this intense radiation, creating strong spectral features that reveal the physical conditions near the core, the velocities, temperatures, and chemical composition of the gas. Despite their immense brilliance, the central regions fueling the quasar remain incredibly compact, no larger than our solar system. The energy output depends on the rate at which matter falls inward onto the black hole, and this process can vary dramatically over time, leading to fluctuations in the quasar's brightness. Observations of quasars at different distances show how these energetic objects were more common in the early universe, reflecting a period when galaxies were rapidly growing and vigorously feeding their central black holes. Their immense power makes them visible across great cosmic distances, allowing us to peer back through time to a much younger universe. Quasars are silent and brilliant witnesses to galactic youth. Astrobiologists, those quiet seekers of life beyond Earth, study planetary atmospheres with extraordinary care, searching for subtle chemical hints of life. To understand whether a distant world, an exoplanet, might support living systems, researchers examine the gases surrounding it with meticulous precision. When starlight from the host star passes through a planet's atmosphere during an orbit, particularly during a transit, when the planet passes in front of its star, the light carries subtle imprints. These imprints are created by the specific molecules it encounters. Sensitive instruments like spectrographs can separate this light into its component colors, its spectrum, and reveal the presence of specific substances that may indicate biological activity. Oxygen, methane, and other reactive gases are especially interesting because they should vanish relatively quickly from an atmosphere unless a continuous process, actively replenishes them. On Earth, living organisms maintain many of these gases in our atmosphere through constant interaction with the environment. Photosynthesis, for instance, produces vast amounts of oxygen. Microbes produce methane. Astrobiologists combine atmospheric models, laboratory experiments, and observations across many wavelengths to determine whether unusual chemical mixtures could arise from natural geological or chemical processes alone. or if they might require something more dynamic, something biological. Their work demands caution and careful interpretation, because planets can produce surprising chemistry without the presence of life. Volcanic activity, or photochemical reactions driven by stellar UV light, can also generate interesting atmospheric compositions. Even so, each newly analyzed atmosphere, each faint spectral fingerprint, adds to a growing library of possibilities for life in the universe. This expanding knowledge helps refine the search for planets that might host stable climates, the presence of liquid water, and long-lasting cycles of elements that could support biology in forms familiar or entirely unfamiliar to us. They are silent and patient detectives in the cosmic quest. The surfaces of some moons, those icy companions in the outer solar system, are constantly reshaped by cryovolcanic eruptions. They are cosmic geysers, spewing icy material. These moons contain interiors that remain warm enough to keep certain materials melted beneath their icy crusts. Instead of molten rock, as found in terrestrial volcanoes, their hidden reservoirs contain mixtures of water, ammonia, nitrogen, or other volatile substances, compounds that remain liquid at the extremely low temperatures found in the outer solar system. Pressure builds as these subsurface oceans and chambers shift and churn under the influence of tidal forces from their parent planet. When pathways open through cracks or weak points in the thick ice, pressurized material escapes in plumes that rise into space or cascade across the surface. These eruptions are not fiery, but icy, spewing slush and vapor. Over time, these repeated eruptions create smooth plains of newly deposited ice, or intricate ridges and mottled textures that constantly replace older terrain. The resurfacing process can hide impact craters and erase geological features that would otherwise preserve a long history of surface events. Enceladus and Triton, a moon of Neptune, are prime examples of cryovolcanically active worlds. Observing these ever-changing landscapes teaches scientists how internal heat, tidal forces, and complex chemistry maintain activity in worlds far from their stars. The presence of liquid environments beneath the surface also raises profound questions about what forms of life might exist in these protected, energy-rich habitats. They are silent and dynamic worlds full of hidden potential. Gravitational lensing, that cosmic optical illusion, can magnify galaxies so distant that they would otherwise remain completely invisible. It is a natural telescope built by gravity itself. As light travels across the cosmos, it moves through regions profoundly shaped by the distribution of mass. When a massive object, such as a galaxy cluster, lies along the line of sight between an observer and something far, far beyond, the curvature of space around that mass alters the path of passing photons. The fabric of space-time bends, and with it, the light. The effect can stretch, brighten, or multiply the appearance of the background galaxy. Instead of a single, faint smudge, the observer may see luminous arcs or even complete rings that precisely trace the bending of the light. This magnification allows astronomers to study structures that formed when the universe was young and very different, revealing details about star formation rates, dust content, and the assembly of early galaxies. By analyzing how the light is distorted, researchers can map the distribution of mass within the lensing object, including any dark matter that emits no light but exerts a powerful gravitational pull. This technique provides a crucial tool for understanding the mysterious nature of dark matter. Each lensing event becomes a natural telescope built by gravity itself, offering a rare view of regions too distant or too faint for direct observation with our conventional instruments. These cosmic lenses are silent windows into the universe's deepest past. Young stars, those nascent suns, flicker unpredictably as dust clouds drift across our line of sight. They are cosmic newborns shrouded in a veil of changing shadows. In stellar nurseries, those vast and dusty clouds where stars begin their lives, gas and dust remain abundant. Young stars often possess swirling disks of leftover material. These protoplanetary disks are the birthplaces of future planets, moons, and smaller bodies. Clumps within these disks, or even irregularities in the disk itself, can pass between the star and our observatories here on Earth, blocking or dimming the star's light. The resulting fluctuations in brightness may follow no obvious pattern, no regular cycle, because the dust distribution is constantly shifting under the influence of stellar winds, magnetic fields, and gravitational forces from the forming planets within the disk. Some stars dim slowly and then brighten quickly in a sudden burst, while others show a chaotic sequence of unpredictable changes. These patterns of flickering offer crucial clues about the intricate structure and dynamic behavior of the disks surrounding them. By studying this flickering light, scientists can detect the presence of rings and gaps carved out by forming planets. They can identify warps and regions where material accumulates. The variations also help to identify potential planets forming within the disks as their gravitational effects subtly shape the dust. These early changes reveal the dynamic environment in which solar systems take their first steps toward maturity. They are silent and flickering stories of planetary birth. Some galaxies, those vast and majestic collections of stars, grow by steadily consuming smaller companions. They are cosmic cannibals, slowly absorbing their neighbors. Galaxies do not always evolve in isolation. In crowded, cosmic neighborhoods, large systems frequently encounter smaller ones. Gravity, that universal sculptor, pulls them together, slowly but relentlessly, causing the smaller galaxy to lose stars and gas as it spirals inward towards its larger devourer. Streams of material, stars, and gas are stretched out behind the smaller galaxy, leaving luminous trails that mark the path of the cosmic meal. These tidal streams are often remarkably long and diffuse, difficult to detect, but revealing the history of the interaction. These mergers, even minor ones, can trigger bursts of intense star formation. As gas clouds within both galaxies collide and compress, sparking the birth of new suns. Over long periods, the larger galaxy incorporates the stars of its companion, adding to its halo and inner regions, slowly growing in size and complexity. The chemical signatures of these absorbed stars often differ slightly from those already present in the larger galaxy, allowing astronomers to trace the history of past mergers, like forensic evidence written in starlight. This process of gradual growth plays a major role in shaping the structure of galaxies and helps explain why many exhibit complex layers, extended halos, and subtle variations in their stellar populations. Each consumed companion becomes part of a larger whole, its identity preserved only in faint remnants, and the chemical fingerprints of its stars. They are silent and profound testaments to the dynamic and often violent evolution of galaxies. The atmospheres of some exoplanets, those distant and mysterious worlds, glow faintly as they heat up in the intense starlight, of their parent stars. They are cosmic lanterns, shining with borrowed warmth. When a planet orbits close to its star, intense radiation from the star warms its atmosphere to temperatures far higher than anything found on Earth. The excited molecules and atoms in the atmosphere then re-emit this absorbed energy in the form of a delicate glow, often detectable at infrared or even visible wavelengths. This emission reveals crucial details about the gases present, their temperatures, and the dynamic behavior of the atmosphere. In some cases, the glow shifts across the surface as powerful winds redistribute heat from the scorching day side to the cooler night side, creating a dynamic and ever-changing thermal map. Certain planets display chemical reactions triggered by ultraviolet light from their stars, producing compounds that contribute additional brightness to their atmospheric glow. By observing these faint emissions during different phases of the orbit, scientists can reconstruct weather patterns, thermal gradients, and atmospheric circulation on worlds that remain unresolved as single points of light. The soft radiance that surrounds these planets offers a precious window into environments shaped by intense stellar energy. They are silent and luminous clues to the extreme conditions of distant worlds. Planetary nebulae, those ethereal and colorful clouds of gas, mark the final breaths, the peaceful farewells of medium-sized stars. Stars not unlike our own sun. When stars, similar in mass to the sun, reach the ends of their lifetimes, they shed their outer layers. This process occurs through slow winds of gas and gradual pulsations over tens of thousands of years. As these layers drift outward, the hot core left behind, the nascent white dwarf, illuminates them with intense ultraviolet light. The gas responds by glowing in vivid colors that precisely trace the composition and density of the expanding shell. These shapes can become perfect rings or elegant ovals, or intricate patterns, depending on the star's rotation, the influence of its magnetic fields, or interactions with a nearby companion star. The Ring Nebula and the Helix Nebula are iconic examples of these beautiful structures. The nebula expands over time, gradually thinning until it fades into the background of interstellar space. The exposed core, the white dwarf, slowly cools and dims, becoming a compact remnant that will shine faintly for billions of years. Planetary nebulae provide valuable insight into how stars recycle material back into the galaxy, enriching future generations of stars and planets with heavier elements. Elements that were forged in the star's core during its life. Each one represents a peaceful transition from active stellar life to a quiet and serene final stage. They are silent and colorful testaments to cosmic renewal. Supermassive black holes, those colossal and enigmatic objects at the centers of most galaxies, can regulate star formation across entire galaxies. They are cosmic conductors controlling the rhythm of stellar birth. At the very centers of many galaxies, enormous black holes, millions or even billions of times the mass of our sun, gather material into swirling disks. When the inflow of gas and dust becomes vigorous, the region near the core releases tremendous amounts of energy. This energy travels outward through powerful jets, strong winds, and intense radiation. These outflows heat the surrounding gas in the galaxy's halo and bulge, and can push it away from the central regions. If the gas becomes too warm or too diffuse, it cannot collapse under its own gravity to form new stars. In this profound way, the central black hole influences the pace of growth across the entire galaxy. It acts as a feedback mechanism, controlling the galaxy's stellar birth rate. Galaxies with very active centers, known as active galactic nuclei, often show reduced star formation in their inner regions, while those with quiet centers, whose black holes are not actively feeding, may continue forming stars at a steady rate. This connection reveals a delicate balance between feeding the central black hole and allowing the galaxy to build new stellar populations. It is a cosmic seesaw balancing destruction and creation. Understanding this relationship, this intricate interplay, helps explain why galaxies differ so much in appearance, in behavior, and in their long-term evolution. Some become red and dead, elliptical galaxies, with little to no ongoing star formation, while others remain blue and vibrant, spiral galaxies, constantly renewing their stellar populations. Supermassive black holes are silent and powerful architects of galactic destiny. Some stars, those distant and individual points of light, orbit the galactic center on paths tilted far above the flat and familiar disk of the Milky Way. They are cosmic high flyers tracing a three-dimensional path through our galaxy. Most stars in our Milky Way follow orbits that stay within the thin and relatively flat disk of the galaxy, like cars on a cosmic racetrack. But a significant number travel on paths that rise high above or dip far below it. These inclined or highly eccentric orbits can result from ancient interactions with other galaxies, from mergers with smaller dwarf galaxies, or from gravitational disturbances caused by massive objects within the Milky Way itself, like giant molecular clouds or dense star clusters. As stars move along their inclined paths, they offer a unique three-dimensional view of the galaxy's structure. Their motions help astronomers to map the distribution of mass throughout the galactic halo, including the elusive and invisible dark matter that cannot be seen directly, but whose gravitational pull dominates the outer regions of the galaxy. Some of these high-flying stars may be remnants of long-absorbed dwarf galaxies, preserving chemical signatures that differ from the stars born within the main disk population. Their elemental composition is a fossil record of their ancient origins. Their unusual orbits reveal the dynamic history of the Milky Way, showing how past events shaped a structure that now appears stable and serene. These stars are silent witnesses to our galaxy's tumultuous growth. Shock waves from supernova explosions, those powerful and destructive fronts, can trigger new waves of star formation, turning cosmic destruction into a spark for new creation. When a massive star explodes in a spectacular supernova, the expanding blast sends a powerful shock wave rippling outward into the surrounding interstellar medium. This shock wave pushes into nearby molecular clouds, compressing the gas and dust, increasing the density in regions that were previously too diffuse to collapse under their own gravity. If the compression reaches a critical threshold, gravity takes over and the cloud begins to contract. New stars then begin forming in the wake of the explosion, turning destruction into creation. This process helps renew regions of the galaxy and contributes to the cycling of material between generations of stars. The heavy elements forged in the supernova are incorporated into the new stars and their planetary systems. By observing these triggered sites of star formation, scientists can follow the intricate chain of events linking the dramatic death of one star to the vibrant birth of many others. The precise timing, the distinct shapes, and the specific locations of these new clusters provide clues about how the shock wave traveled and how far its influence extended. These interactions illustrate the profound interconnectedness of cosmic processes, where the end of one stellar life becomes the powerful spark for countless new beginnings. Supernova shock waves are silent and powerful catalysts of cosmic regeneration. Some binary stars, those stellar pairs, are so incredibly close that one literally pulls material off the surface of the other. They are cosmic vampires locked in a dance of mutual sustenance. In these remarkable systems, the two stars orbit each other at such short distances that their gravitational fields overlap in a delicate but powerful balance. As one star expands during its evolution, its surface can swell beyond the region where its own gravity remains dominant. This gravitational boundary is called the Roche lobe. When this happens, gas from the outer layers of the donor star drifts toward its companion, forming a flowing bridge of material suspended between them. This stream of gas then typically gathers around the receiving star, forming a spiraling disk known as an accretion disk. This disk grows hotter and denser as more material arrives and spirals inward toward the companion star's surface. This mass transfer can dramatically alter both stars' evolutionary paths. The donor star becomes stripped of its outer layers and can reveal deeper layers that would normally stay hidden, while the companion grows in mass and luminosity, appearing rejuvenated or even more massive than it was at birth. Sudden bursts of brightness can occur when the accreted gas heats rapidly or undergoes explosive nuclear reactions on the surface of the companion star. These events can manifest as novae or even as recurrent novae, where the same system erupts multiple times. These complex interactions help scientists understand how close companionship can reshape the lives of stars in ways that solitary stars never experience. They are silent and dynamic stories of stellar symbiosis. Cosmic dust grains, those tiny and ubiquitous particles traveling through space, can contain crystalline structures forged in the hearts of dying stars. They are microscopic archives of stellar alchemy. These tiny particles of cosmic dust travel through interstellar space, carrying the indelible signatures of the environments where they formed. In the outer layers of aging stars, as the star sheds material into its surroundings, gas cools and condenses into solid grains. Under the right conditions, atoms within this cooling gas align themselves into orderly, repeating patterns that create crystals with unique chemical fingerprints. These are often silicate crystals or carbonaceous dust grains. Supernova blasts and powerful stellar winds from massive stars then scatter these grains across the galaxy, mixing them into vast clouds of gas and dust that will eventually form new stars and planets. When scientists analyze the light reflected or absorbed by dust, they detect subtle features in the spectrum that reveal the presence of these crystalline structures. Some grains found in meteorites that have fallen to Earth are older than the solar system itself, making them pre-solar grains, relics of long-vanished stars. Their composition helps trace the cycle of material from one generation of stars to the next, showing how the universe continuously recycles the building blocks of planets and possibly even the ingredients for biology. These dust grains are silent and microscopic messengers from the stellar past. Stellar nurseries, those vibrant and active regions of star birth, can form intricate networks of luminous filaments. Filaments filled with newborn suns. They are cosmic tapestries woven from gas and dust. Within dense clouds of gas and dust, gravity, that relentless sculptor, gathers material into long strands or threads. These filaments weave through the darkness like luminous threads or intricate veins in a cosmic leaf. These filaments act as natural highways for matter to flow into regions where stars are beginning to form. As gas accumulates along these filaments, knots or denser clumps develop, each one gradually growing hotter and denser. Eventually, these knots collapse under their own gravity and ignite as young stars, often surrounded by swirling disks of leftover material, the protoplanetary disks. The filaments themselves may twist and bend under the influence of magnetic fields and turbulent motion within the cloud, creating a dynamic and ever-changing tapestry of shapes that shifts slowly over time. Observations at multiple wavelengths, from radio waves to infrared light, reveal how material moves through these networks, and how different temperatures highlight distinct structures within the gas. These nurseries provide a precious view of the earliest stages of stellar development, showing how interconnected processes create entire clusters of stars rather than isolated individuals. Each glowing thread marks a pathway through which the galaxy continues to renew itself. They are silent and vibrant paintings of cosmic genesis. Some planets, those colossal and mysterious worlds, develop thick atmospheres of hydrogen, envelopes so vast that they dwarf their rocky cores. They are cosmic balloons inflated with light gases. These enormous envelopes form when a young planet grows rapidly enough to capture and retain light gases, primarily hydrogen and helium. This occurs before the surrounding disk of gas and dust from which the planet formed disperses into space. Hydrogen and helium flow toward the growing world and accumulate in quantities far exceeding the mass of the rocky material beneath. Over time, the atmosphere becomes a vast layer extending high above the core, blending continuously from dense, lower regions where hydrogen can become liquid or even metallic into the thin, outer edges that gradually merge with interstellar space. Temperatures and pressures inside this envelope can reach extreme levels, producing exotic forms of chemistry not found in smaller terrestrial planets. Winds move through the atmosphere at tremendous speeds, carrying heat from one region to another, and creating dynamic weather patterns that may span the entire planet. Even though the rocky core remains hidden from view, the atmosphere reveals much about the planet's history and environment. It preserves clues about the early stages of formation, helping researchers understand how planets grow and why some accumulate far more gas than others. The chemical fingerprints in starlight can reveal the precise composition of distant worlds. They are cosmic detectives, reading the atmospheric signatures of exoplanets. When a planet passes in front of its star, an event known as a transit, a small portion of the starlight filters through the planet's atmosphere before reaching our observatories. Each type of atom or molecule in the atmosphere absorbs specific colors of light at particular wavelengths, leaving a series of subtle but distinct patterns in the star's spectrum. By analyzing these patterns with sensitive instruments, scientists can infer the presence of specific gases that may hint at climate, weather, or even geological processes on the distant world. The technique works even for planets that cannot be directly imaged, allowing researchers to explore worlds far smaller and cooler than previously possible, as data accumulate from numerous exoplanet transits. Comparisons between different planets reveal trends in atmospheric chemistry. Trends that reflect formation history and environmental conditions. These fingerprints provide a method for examining worlds across the galaxy using nothing more than the light they allow to pass through their atmospheres. This approach represents one of the most powerful tools for studying distant atmospheres without sending probes or missions to the worlds themselves. They are silent and profound windows into the hidden chemistry of alien skies. Relics of ancient galaxies remain scattered throughout the vast expanse of the Milky Way. They are cosmic ghosts, whispering stories of past mergers. Long ago, smaller galaxies, dwarf galaxies, drifted close enough to the immense gravitational pull of the Milky Way. Instead of surviving intact, many were slowly, but relentlessly, torn apart by tidal forces as they spiraled inward. Their stars stretched into elongated streams that wrap around the galaxy like faint trails of stardust. These remnants, these stellar streams, remain visible as thin ribbons of light, tracing the orbits of the long, consumed systems. Each stream carries a distinct chemical signature that differs from the stars born within the main disk of the Milky Way, allowing astronomers to identify their ancient origins. By mapping their precise paths, researchers can reconstruct the merger events that shaped our galaxy over billions of years. Some relics appear as faint clusters still holding together, barely bound, while others have dispersed into the broader halo of the Milky Way. Together, they form a vast historical record, preserved in starlight, revealing how the Milky Way grew by gradually absorbing its smaller neighbors. They are silent and luminous testaments to our galaxy's tumultuous past. Some stars are surrounded by dusty disks left over from the process of planet formation. These are cosmic construction sites, where worlds are slowly taking shape. After planets form within swirling disks of gas and debris, leftover material often remains in orbit around the central star. Collisions between smaller bodies, such as asteroids and comets, continually grind fragments into fine dust. This dust then spreads across the system, forming a debris disk. This dust absorbs starlight and then re-emits it at longer wavelengths in the infrared, creating a distinctive signature that can be detected with specialized telescopes. The structure of these disks varies depending on the presence of planets, which can carve gaps in the disk, shepherd rings of dust, or scatter material into new configurations. Observing the distribution and temperature of the dust reveals the intricate architecture of the system and helps identify regions where planets might still be forming. Over time, radiation pressure from the star and continued collisions gradually remove the material. But some disks can persist for hundreds of millions of years. These dusty rings act as archives of early planetary history, offering clues about the processes that shape the worlds orbiting the central star. They are silent and glittering records of planetary youth. Intergalactic gas, that incredibly diffuse and almost invisible material, can stretch in narrow filaments that connect distant clusters of galaxies. They are cosmic threads weaving the universe together. Across the universe, matter is not evenly distributed. Instead, it collects into vast structures that form a cosmic web on the largest scales. This web consists of clusters of galaxies, dense nodes of matter, and connecting strands or filaments. These filaments consist of diffuse gas, primarily hydrogen, enriched with elements forged in earlier generations of stars. Though extremely faint and difficult to detect, they span enormous distances between galaxy clusters and help channel material into growing galaxies. Observations from powerful telescopes reveal that these filaments guide the motion of galaxies and influence how clusters evolve over cosmic time. As gravity pulls matter along the strands, interactions between the diffuse gas and the invisible dark matter shape the growth of these large-scale structures. Studying these filaments requires sensitive instruments that can detect subtle signals from hot or ionized gas. Their existence confirms theoretical models of cosmic evolution and demonstrates how the universe organizes itself on the largest scales. Through them, galaxies receive the raw material needed to form new stars and continue expanding their stellar populations. They are silent and invisible architects of the cosmic web. Cosmic magnetic fields, those invisible but powerful forces, can influence the motion of charged particles across huge distances. They are cosmic compasses, guiding the flow of energy. These fields arise from the motion of conductive plasma within stars, galaxies, and the diffuse intergalactic gas. Once established, they create invisible pathways that guide the movement of electrons and ions. Charged particles spiral along the magnetic lines, often traveling great distances while emitting radiation that reveals their presence. This radiation is known as synchrotron emission. The strength and orientation of these fields vary from place to place across the cosmos, shaping the behavior of cosmic rays, those high-energy particles that constantly bombard Earth, and affecting the intricate structure of nebulae and the powerful jets that erupt from active galactic nuclei. In regions with complex magnetic activity, particles can become trapped in magnetic loops or channeled into narrow beams that stretch far from their origins. Understanding these interactions helps astronomers to trace the flow of energy in gravity, gas pressure, and magnetic forces all play significant and interconnected roles. The influence of magnetic fields demonstrates how even unseen forces contribute to the dynamic and ever-changing nature of the universe. They are silent and invisible sculptors of the cosmic plasma. Some planets, those enduring worlds, orbit dead stars that emit little more than faint, ghostly light. They are cosmic survivors, circling fading embers. When a star of moderate mass completes its life cycle, it sheds its outer layers and leaves behind a compact remnant, a white dwarf that slowly cools over time. These remnants produce only a dim glow, the residual heat of a dying star. Yet, some continue to host planets that survived the dramatic transformations of their parent stars. The faint light from the white dwarf offers minimal warmth, creating environments far colder than those around ordinary main sequence stars. Any surviving planets may have experienced intense heating during the earlier phases when their star expanded into a red giant, followed by long periods of deep freeze as the stellar remnant slowly faded. Some planets might orbit so closely that they experience strong tidal forces from the dense white dwarf, while others drift farther out in the perpetual cold. Studying these systems reveals how planetary bodies can endure extreme changes and adapt to evolving stellar conditions. Their continued existence shows that planets can persist even after their stars cease shining brightly. They are silent and resilient testaments to planetary survival. The atmospheres of some gas giants, those colossal worlds, glow in infrared wavelengths. They are cosmic radiators shining with internal heat. Deep within these enormous worlds, heat rises from the interior and slowly escapes through thick layers of gas. Much of this heat is released as infrared light, which is invisible to human eyes, but perfectly detectable by specialized instruments. The glow forms because the gases in the atmosphere absorb energy from the interior and later release it as gentle radiation. This steady output can reveal the temperatures, motions, and chemical makeup of the atmosphere. Winds carry heat across the vast surfaces, shaping patterns that shift slowly over time. In some giants, powerful storms stir the gases so deeply that warm regions rise from the interior and shine more brightly than their surroundings. Jupiter's great red spot, for instance, is warmer at its center than the surrounding clouds. Observing this faint infrared light allows scientists to study the hidden workings of planets that remain distant points in the sky. These glowing atmospheres show how energy moves through deep layers of swirling hydrogen and helium, providing a glimpse into environments that dwarf the scale of any weather system on Earth. They are silent and luminous windows into the inner lives of gas giants. Tidal interactions, those powerful and subtle gravitational tugs, can twist stellar envelopes into elongated shapes. They are cosmic dancers, reshaping each other through gravitational embrace. When two stars orbit close to each other, their mutual gravity pulls strongly on their outer layers. The tug is not uniform across the star's surface, because the near side experiences a stronger pull than the far side. Over time, this uneven pressure shapes the outer region into a form that stretches along the line connecting the two stars. The star becomes slightly elongated rather than perfectly round. It takes on a prolate spheroid or egg-like shape. This distortion changes gradually as the stars move in their orbits, creating subtle shifts in brightness that reveal the stretching. In some systems, the effect becomes strong enough to influence how the star rotates and how energy moves within its interior. The twisted shape may also alter how the star sheds material, or how it exchanges gas with its companion in a binary system. These interactions demonstrate how gravity can sculpt stars, just as it shapes planets and galaxies, leaving behind visible signatures that reveal the powerful forces at work. They are silent and profound testaments to the pervasive power of cosmic tides. Some galaxies, those vast and intricate structures, host enormous cavities, hollowed-out regions where past explosions cleared out vast amounts of gas. They are cosmic bubbles, carved by stellar violence. Within certain galaxies, observations reveal huge, hollowed-out areas, regions that appear strangely empty compared to their surroundings. These cavities are thought to form when powerful events release enough energy to push gas outward from the galactic center or disk. Exploding stars in supernovae, energetic outflows from a central black hole, or bursts of intense star formation can all send shock waves racing through the galactic environment. As these shock waves expand, they sweep away gas and dust, leaving behind large bubbles or cavities. These structures remain visible long after the original event that created them has faded. The size and shape of each cavity records the history of the forces that created it. Over time, the bubbles may stretch, fragment, or slowly refill as new material drifts inward from other regions of the galaxy. Studying these features reveals how galaxies regulate their supply of gas, and how energetic events influence future star formation. Each cavity represents a moment of dramatic change that reshaped its host galaxy from within. They are silent and powerful records of galactic upheaval. Interstellar clouds, those cold and dark reservoirs of cosmic material, can freeze molecules onto dust grains in icy layers. They are cosmic freezers, preserving molecular complexity. In the coldest regions of space, temperatures fall so low that gases behave in unusual ways. Molecules drifting through these dark clouds can become trapped on the surfaces of tiny dust particles. Once attached, they form thin icy coatings that build up layer by layer over long periods. These frozen layers often contain water ice, carbon dioxide ice, methane ice, and other volatile compounds that remain solid in frigid conditions. As cosmic rays, those energetic particles from deep space and faint ultraviolet light pass through the cloud, they trigger slow chemical reactions within the ice. These reactions create more complex molecules, enriching the cloud with material that may later participate in the birth of stars and planets. Amino acids and other organic molecules can form on these icy mantles. When the cloud eventually collapses to form new stars, the heat from the forming stars evaporates the ice and releases its chemical inventory into the surrounding gas. These icy grains act as tiny storage sites that preserve the earliest stages of chemical evolution in the galaxy. They are silent and microscopic testaments to the universe's capacity for prebiotic chemistry. Stellar mass black holes, those enigmatic and profoundly dense objects, can form when massive stars collapse. They are cosmic devourers born from stellar death. A star many times larger than the Sun spends its life fusing heavy elements in its core, until the nuclear reactions can no longer support its immense weight. When the outward pressure from fusion fails, gravity pulls the core inward with overwhelming force. The collapse proceeds so quickly that the core becomes an object of extraordinary density. If nothing can stop the contraction, if the core's mass exceeds a critical limit known as the Tolman-Oppenheimer-Volkoff limit, the core turns into a black hole, an object with a mass similar to that of the original star, but compressed into a much smaller volume, a singularity. The outer layers of the star may blast outward in a dramatic supernova explosion, while the black hole remains behind as a silent and invisible remnant. Although it emits no light of its own, its presence becomes visible through its profound effect on surrounding matter. Gas from a nearby companion star or from an interstellar cloud spirals toward it, heating up to extreme temperatures and producing radiation that can be detected from across the galaxy in X-rays and gamma rays. These remnants show how the death of a single massive star can produce one of the most extreme objects in the universe. Stellar mass black holes are silent and powerful reminders of the universe's capacity for ultimate collapse. The surfaces of neutron stars, those incredibly dense and compact remnants, contain matter packed at astonishing densities. They are cosmic diamonds of unimaginable weight. After certain stars explode in supernovae, their cores collapse into compact spheres, composed mostly of neutrons. These neutrons are crowded together more tightly than any material found on Earth. The surface appears solid, yet the matter within it is unlike anything in ordinary experience. It is a state of degenerate neutron matter. At the topmost layer, atoms are squeezed into a state where electrons have combined with protons to form neutrons, leaving a crust of neutron-rich material sometimes referred to as a nuclear pasta, due to its complex and exotic structures. Deeper within, the density becomes so extreme that the properties of matter remain a subject of active research. Scientists are still trying to understand the exact equation of state for this super dense matter. The gravity at the surface is so intense that even a small irregularity, a tiny bump on the surface, could weigh countless tons if brought to Earth. When these stars rotate or undergo internal changes, stresses can build in the rigid crust, until sudden adjustments, star quakes, release bursts of energy detected as short flashes of radiation. By studying these signals, scientists learn more about the internal structure of neutron stars and the behavior of matter under conditions impossible to reproduce on Earth. Neutron stars offer a unique laboratory for probing and the fundamental nature of the universe. They are silent and profound testaments to the extremes of cosmic physics. Some exoplanets, those distant worlds, orbit in chaotic systems where gravitational pulls constantly shift their paths. They are cosmic pinballs bouncing in a gravitational game. In certain star systems, multiple planets move so closely to one another that their mutual influences never settle into a stable and predictable pattern. Each orbit produces subtle tugs that accumulate over time, altering the shape and tilt of the paths each planet follows. The result is a dynamic environment where predictions become challenging even for advanced models. Some planets may drift slowly inward or outward over millions of years, while others may change their orbital shapes in cycles that play out over long periods. The interactions can become so strong that one planet may eventually be flung into a new region of the system or even ejected entirely into interstellar space. Observations of these chaotic systems reveal just how varied planetary architectures can be. They show that not all systems resemble the orderly layout seen in our solar neighborhood. Instead, the galaxy contains environments where gravity produces an ever-shifting dance that never fully repeats itself. They are silent and unpredictable ballads of cosmic gravity. Jets from young stars, those energetic outflows of material, can carve long channels through surrounding gas. They are cosmic drills, shaping their birth environments. As a young star gathers material from its surrounding disk, some of the infalling gas becomes channeled by powerful magnetic fields and expelled from the poles of the star at high speed. These narrow streams of material travel outward in opposite directions, plowing into the surrounding cloud of gas and dust.